Welcome students. Today we are going to learn about Z transform calculation for infinite duration signal. Z transform for infinite duration signal. That means the duration of the signal is infinite. So either your discrete time signal xn exists from 0 to infinity or minus infinity to 0 or minus infinity to plus infinity. So we can get these three types of signal. Our discrete time signal can exist from 0 to infinity or minus infinity to 0 or minus infinity to plus infinity. So if it exists from 0 to infinity, that means it is on the positive side only. And if the signal is on the positive side only, then it is a causal signal. Now, if our signal is existing from minus infinity to 0, that means the signal exists only for negative values of n, or it exists only on negative side. So it is an anticausal signal. Now, if our signal exists from minus infinity to plus infinity, that means it exists on both sides for negative values as well as for positive values. So, our signal is non-causal. So, while analysis, we will get these three types of signals: causal, anticausal, and non-causal. These three types of signals are having different approaches for the calculation. So we will start one by one. Now, if our time domain signal xn is causal and it is of infinite duration, then we can represent that discrete time signal as an un, where a is some constant, as a to the power n. We are having signal component as a to the power n. So it will exist from minus infinity to plus infinity, but we are multiplying this signal with the unit step signal. Unit step signal means a signal which is having the value of 1 if n is greater than or equal to 0, and it is having the value of 0 for n less than 0. So, because of this multiplication, this combined signal will exist from 0 to infinity, because unit step exists from 0 to infinity. So, we are multiplying an with un. So, this overall signal will exist from 0 to infinity. So, it's a causal signal. Now, for getting the Z transform of this signal, we will use the standard Z transform formula, that is summation from minus infinity to infinity xn z to the power minus of n. Now, we will put the value of xn, our signal, in this equation. So, we will get an un z to the power minus of n. Now, this unit step signal exists from 0 to infinity. So, now our range of summation will change. It will become summation from n is equals to 0 to infinity. Now, in this range, 0 to infinity, in this range, the value of unit step signal is 1. So, we will get the signal as an into 1. So, no need to write 1. So, now we can write it as an. So, the signal is an. The formula part is z to the power minus n. We can simplify these two terms by combining them and writing it again as this is a z inverse to the power n. Now, if we expand this signal For n is equals to 0, 1, 2 and so on. So for 0 we will get az inverse to the power 0. For 1 we will get az inverse to the power 1. For 2 az inverse to the power 2 and so on. Up to where? Up to infinity. So we will get a series like this. If we simplify this series, then a z inverse to the power 0 means 1 plus a z inverse plus a z to the power minus 1 to the power 2 a z inverse square up to infinity. We will get a series like this. So we are writing it as equation number 1. Now we are getting a series for xz which starts from 1 and reaches up to infinity. So how to get the answer for this series? As you can see, the common ratio, the ratio with which we multiply the next number, the common ratio is az inverse. We are multiplying the previous term with az inverse to get the next term. So this kind of series are basically GP. In GP, the form of equation, the form of summation that we get is 1 plus r square plus r cube. If it is infinite GP, then the terms will reach towards infinity. So we are getting one infinite GP for the result of xz. Now how to find the answer? We are getting xz as 1 plus az inverse plus az inverse square and so on. Now if the series is infinite GP, 1 plus r square plus r cube and so on up to infinity. Now the series is infinite GP. The result of this series will be finite only when the value of r is less than 1. If this value of r is common ratio. So if the value of common ratio is greater than 1, then after adding these all terms, we will get infinity. So that is not a result for us because we want finite results. So for getting a finite result, the value of r should be less than 1. This you have to keep in your mind, that whenever you are solving with the infinite GP, then always you will get the finite result only when the value of common ratio is less than 1. In that case, what will be the result? The result will be 1 upon 1 minus r. This will give you the result. So, how to use these two things in Z transform? This condition will tell you the region of convergence for Z transform. This condition will give you the value of Z transform. So, these both will be used, one for region of convergence and one for Z transform. Now we are going to use these things. So in our series, as you can see, the value of common ratio is az inverse. So for getting the finite result, r should be less than 1. So the value of az inverse should be less than 1. That means the value of a upon z should be less than 1 or value of z should be greater than 1. So this will define the region of convergence. This is our ROC for the given numerical. Now what will be the value of z transform? So it has to be 1 upon 1 minus r. R is az inverse. So we will get 1 upon 1 minus az inverse. After simplification, we will get z upon z minus a. So this is the value of Z transform. Now, how to plot the region of convergence? Because we have to plot it in the Z domain. So we will draw, this is A, Z is greater than A. So we will plot a circle with the radius A, this is of the radius A, and the region of convergence is Z greater than A. Z greater than A means the region of convergence is outside of the circle where the value of Z is greater than A. So, we have find the solution of this equation with the help of the concept of infinite GP, whose result is finite only when the value of common ratio is less than 1. And in that case, the value of the series is 1 upon 1 minus r. So, with this concept, we find the region of convergence for our numerical is Z is greater than A, and the Z transform itself is Z upon Z minus A. And the region of convergence is outside the circle with the radius A. So this is when our signal is causal. The whole explanation that we have seen by now is for a causal signal. Now what if in that case our signal is existing at the negative side only, not in the positive side of index? So we can take an example of anticausal signal. Suppose it is BNU minus N minus 1. This UN minus U minus N minus 1 shows it is a unit step signal which exists from minus 1 and goes up to minus infinity. So it is less than or equal to minus 1. The value of the signal is 1, and otherwise the value is 0. So this will start from minus 1 and it will move towards minus infinity. It will reach up to minus infinity in fact. So this is B is a constant. So Bn will exist from minus infinity to plus infinity, but we are multiplying this Bn with U minus N minus 1. So the whole signal will exist from minus 1 to minus infinity, because we are multiplying Un with b to the power n with U minus N minus 1. So the signal will exist from minus 1 to minus infinity. Now when we are going to calculate the Z transform, the standard formula is again summation from minus infinity to plus infinity xn z to the power minus of n. Now our signal exists from minus 1 to minus infinity. So the range of summation is from n is equals to minus 1 to minus infinity, or minus infinity to minus 1 you can write. It doesn't matter how you have added the signal from starting to end or from end to starting. It doesn't matter. So I have written it as n is equals to minus 1 to minus infinity. The signal xn is bnu minus n minus 1. But from the minus 1 to minus infinity, u minus n minus 1 is 1. So no need to write it. The rest part of the signal is z to the power minus n. Now we can simplify this equation by combining these both terms. So we will get minus 1 to minus infinity b z inverse to the power n. Now the index is in negative n. So we can make the index positive by replacing the variable m, which is equals to minus of n. In that case, the xz will become summation. Now n is from minus 1 to minus infinity. So m will be 1 to infinity. This is b z inverse to the power minus of m, because we are putting n here. So that will become minus of m. Or we can further simplify it as summation from m is equals to 1 to infinity b inverse z to the power m. Now we find that xz is having the pattern of b inverse z to the power m. Now we will expand xz, which is equals to summation from 1 to infinity b inverse z to the power m. Now for different values of m is equals to 1, then we will get b inverse z, plus m is equals to 2, we will get b inverse z square, 3 b inverse z to the power 3, and so on. Now we can take b inverse z out of the bracket and write the rest of the equation inside the bracket as 1 plus b inverse z plus b inverse z square plus so on. The series will go up to infinity. Now we are again getting one infinite GP series. So the result of this infinite GP will be finite only when the value of common ratio is 1. In our case, in this case, the value of common ratio R is B inverse Z. So we will get the finite result only when B inverse Z is less than 1 or Z is less than B. So the region of convergence will be defined by Z less than B, value of B. This will tell us the region of convergence. Now what will be the value of Z transform then? Again, according to infinite GP, if the result is bounded by the finite condition, then it will be 1 upon 1 minus R. R is B inverse Z. So the result of this complete GP will be 1 upon 1 minus B inverse Z. Outside we are having B inverse Z, so I am writing it here. Now we will simplify this equation. Then we will get this is Z upon B minus Z. So this will give us the Z transform, that is Z upon B minus Z. So now how to plot the region of convergence? For plotting the region of convergence, we will draw a circle with the radius of B. So this is the circle with the radius of B. Now the value of Z is less than B, means the region of convergence for the signal is inside the circle where the value of Z is less than B. So the region of convergence is inside the circle of radius V. This analysis is for anticausal signal. So now we can see when the signal is causal, the region of convergence is outside the circle, and when the signal is anticausal signal, the region of convergence is inside the circle. So this is how we can estimate the Z transform when our signal is causal or when our signal is non-causal, means it is having some positive part and some negative part, or we can say it exists from minus infinity to plus infinity. So in that case we will get a causal part as well as one anti-causal part. So we are taking an example. Suppose xn is equals to an un plus bn u minus n minus 1. Now we have combined one causal signal with one anti-causal signal, and as our signal is having causal as well as anti-causal part, so it is a non-causal signal. Now we can also combine the analysis that we have done till now. This causal signal will have the Z transform as Z upon Z minus A, with the region of convergence Z is greater than A. And This anti-causal part will have the Z transform as Z upon B minus Z with the region of convergence Z is less than B. Using linearity property, which says that if the signal can be represented by two or more smaller signals, combination of two or more smaller signals, then we can combine the Z transform to get the resultant Z transform of this signal. So we have taken the Z transform of this causal signal, that is Z upon Z minus A. We have taken the Z transform of this anti-causal signal, which is Z upon B minus Z. These things we have already derived in this lecture. And this is having the region of convergence as Z is greater than A. This is having the region of convergence as Z is less than B. Now the main thing is how we can find the resultant region of convergence. The resultant region of convergence can be found by combining these two equations of region of convergence, which says that Z is greater than A, but it is less than B. So we can combine these equations as Z is greater than A but less than B. So now while plotting, what we are supposed to make? We have to make two circles. Now circle with the radius A will be smaller and circle with the radius B will be bigger because Z is greater than A and less than B. So we will plot a smaller circle with the radius A. We will plot a bigger circle with the radius B. Now Z is greater than A. So for this causal system, the region of convergence will be outside of the circle. So we are putting this hashing outside this circle. Now Z is less than B. So for anti-causal signal, the region of convergence is inside this circle. So according to anti-causal signal, we are putting these. This is inside the circle. So now the area where both the region of convergence are existing, that condition is existing, is inside these two circles. That is this region which is inside these two circles. So this annular ring which is having both the region of convergence for this signal as well as for this signal, this annular ring will represent the resultant region of convergence. So we can say when our signal is anti-causal, the region of convergence is inside the circle. When it is causal, it exists outside of the circle, and when it is non-causal, then the region of convergence is in the form of annular ring. The region of convergence that you will get in the form of annular ring. So transforms for causal, anti-causal and non-causal signals. In the next lecture, we will take some examples of this type of signals and then evaluate the Z transform for them.